Okay, so let me immediately start with the definition of a group. So we can start with the abstract definition because that's all we need. Then in the examples, we are going to see how we actually meet these kind of a structure, right? So we have a set and an operation. So I'm going to show the operation with O sign for the time being, but later I'm going to express that notation, okay? So it's basically not the set itself, but the set together with the operation that we call as the group, actually, okay? So the operation has to be associative. So basically in the product of 3 or more elements, operation of 3 more elements, the order is not important. Well, the order in which you evaluate these operations is basically is immaterial. Yeah, whatever. I mean, you know what associativity is. So in any case, so that's actually a very critical property, but we don't actually stress on this enough. There are things like non-associative algebras, like the Lie algebras and things like that, in which case this property is not satisfied, but these are actually quite a different kind of objects. In any case, we have associativity. There's a certain element that we call as the identity, which basically doesn't change the element. And then for every element, there's an inverse where this is inverse and operated with the elements itself gives you the identity. Okay, so you can kind of think that every symmetry operation also satisfies that property in a way. So identity is some certain kind of a symmetry that every object has. So that's basically the element, the operation that basically leaves invariant everything. This operation somehow corresponds to application of 2 symmetry transformations, one after the other one. And in any case, for every symmetric transformation, the inverse of the inverse transformation is also a symmetry of an object. So naturally, the symmetry transformations satisfy all of these axioms, okay? Sometimes people add to these basic properties a 4th and a 5th one, like the closedness and things like that. We don't really add these kind of things in here because we're kind of saying that if this is an operation, that this operation is actually closed. So for 2 elements within the group, their product or whatever has to be within the same set necessarily by definition. Okay. In any case, so that's basically the examples. Sorry, is the definition. So there's actually one last property in here. So if it's not a property of the definition of the group, if we have the commutativity property, so if G of H is the same thing as H of G for all G and H within the group, then we say G is abelian or commutative. We're going to use this term a lot. If not, I mean, if there are actually some elements which do not commute with each other, if not, then G is called, I'm going to call them as non-abelian or non-commutative. Okay, we have examples of symmetric groups that of each kind, basically. So as a result, that's not an axiom of the group axioms. It's just another property that some certain groups satisfy and some other groups do not. There are certain things that I need to state. before everything, so I don't want to forget some of them. Yeah, let me first start with some examples, okay? Right. The first kind of examples come from algebra, from mathematics itself. So as a result, for example, the integers together with the addition operation is a, that's integers. So that's the set of integers. So I'm going to use the Z notation in there. So set of integers together with addition is a group. The set of real numbers with addition, complex numbers with addition, or the rational numbers with addition, and things like that. And there are things like real numbers where the zero is subtracted together with the multiplication is a group, or the complex numbers, or the rational numbers and things like that, all right? So these are some examples of groups that we actually get from algebra. And there are some other examples like the matrices, for example, or the vectors and vectors in a vector space together with addition, for example. And matrices satisfy some certain properties with multiplication, for example, matrix multiplication. If we just exclude non-invertible matrices, I'll talk about some of these matrix groups later. So we have examples coming from there. So these are additive groups. Some people just call these as like additive groups, because we use addition in there. And these are called multiplicative. Matrices, you can actually consider the groups depending on what the operation is. It can be both additive or multiplicative, but for vectors in a vector space, the group is basically additive, right? In any case, that's not an important distinction. The distinction is that the group operations in here, for example, the addition of two elements, you have to use this notation explicitly. But for multiplicative, we usually, we sometimes use the dot, for example, for expressing the product. But usually we get lazy and then we just don't use any kind of a symbol like that, okay? That's the only difference between additive groups and the multiplicative groups. Usually, we cannot use this kind of a notation for additive groups because people will get confused. And so as a result, we have to show them explicitly. But in any case, in all of the applications during the whole semester, I'll be using this notation in here, right? So we will use this notation for general groups. And if the group is like a group of matrices, for example, in that case, I'm just going to use, I'm also going to use this notation as well. So I'm not going to spend time in writing the operation symbol in here, right? Unfortunately, I cannot do this for the additive groups. So that's the only complication in here. Okay. So that's the first thing, right? So I'm going to start using this actually immediately, right? Second thing is, let's then talk about these groups in here. So that's a very special group that we sometimes call Zn. So these are basically the numbers starting from 0 and smaller than n. So this Zn together with the addition. So let me just say it like this. This is addition modulo n. This is a group. Okay, so let me say that this is a group. It's actually a very nice group. Which we use a lot in applications. So later I'm going to use some other notation for the same group. I'm going to use this notation, but I'll talk about this later, the meaning of that notation. But I mean, if you just look at the mathematical literature, you're going to see both of these kind of notations to express the same group, okay? And so there are some other things like this. So one interesting group is the nth roots of unity. So I'm just going to call this as UN, but that's not a standard notation. So UN is basically the numbers in the complex plane. So these are complex numbers that has the property of their nth power is equal to 1. Okay. So as an example, for example, let's say U2 is basically the numbers 1 and minus 1. These are the square roots of unity. Right? This is the set of numbers where the squares are equal to 1. And then we have like the cube roots of unity. In that case, there are 3 of them. So yeah, I'm just going to write them down like that. Minus 1/2 plus I squared of 3/2. And then minus 1/2 minus I squared of 3/2. So these are the numbers that we are going to meet a lot. So these are the cube roots of unity. Unity is 1, right? Okay. Well, how did I find this? So that's basically very simple. So UN is basically can be computed as like e to the 2 pi I divided by n, and its powers in general is like the e to the 2 pi I over n multiplied with k, and the last one is e to the 2 pi I over n times n minus 1. Okay. Okay, so basically in complex plane, so that's the complex plane. So I'm going to call this as the x-axis, and that's the y-axis. There's this unit circle in here. All right. So this is the unit circle. That's basically the complex numbers where the modulus is equal to 1. So what's modulus? All right, let me quickly go over this because sometimes people do not know what the meaning is. So you can basically write a complex number like that. I'm going to use star for expressing the complex conjugate. And the modulus is basically is the square root of x squared plus y squared. It's essentially the distance of the complex number from 0. So you can actually think of it like that. So that's the x-axis, this is the y-axis. This is the complex number z, that's the real part, and that's the imaginary part. So this is the modulus. Modulus is that, and that's the angle theta. And we usually write the complex number as is modulus multiplied with exponential of I times theta. So we use this kind of a representation in here. In any case, so the unit circle is basically the set of complex numbers where the modulus is equal to 1. This is also an interesting group. Basically, the products of all the numbers in here with each other gives you another number on the unit circle. So as a result, this forms a group in here. In any case, so we have these points in here on the unit circle, which are all equidistant from each other. So I'm going to show them like that. So This basically shows the case n equals 7, right? All of them are making an equal angle of 2 pi over n. I'm basically using the radian units. So all of these angles are equal to each other. Okay, let me cut the story short. Okay, so these are essentially these numbers in here, right? So that's the number 1, that's the number e to the 2 pi I over n. It has modulus unity, and so on. So these are the numbers where the nth power is equal to 1. So as a result, if I take this, for example, this number in here, let's say zk, so it's e to the 2 pi I over n to the power k. The nth power is equal to e to the 2 pi I k. So it's the kth power of e to the 2 pi I, but e to the 2 pi I is basically 1. So as a result, the nth power of that complex number is equal to 1. Okay. So this is a group too. I mean, all of these are groups, obviously. Sorry about that. So in any case, so for example, U3 would basically consist of these 3 points in here. Okay, so one of them is 1. The other point is in here. So this angle is 2 pi over 3 radians, or 120 degrees. So as a result, this angle is 30 degrees. So you can then show that the real part is -1/2 and the imaginary part is square root of 3 over 2. And so that's our first number. The other number is in here. Okay, so that's e to the 2 pi I over 3. And that's e to the 4 pi I over 3. So in any case, so if you just take the cube of these numbers, you are going to get 1. Why am I talking about this? Sorry, this is the idea in here, right? The group Zn together with the addition operation. So let's just remember this. And the group Un with the multiplication operation. They are actually isomorphic groups. The two groups are the same, sorry. So that's e to the 2 pi I over n to the power n minus 1, right? Both groups are isomorphic. Okay, so I'll talk about the isomorphisms in a moment, in a formal sense, perhaps. But what I'm saying is that these two groups, even though mathematically they are different, so one is just a subset of integers, the other one is just numbers from complex plane. But if you just consider the group operation with each other, they have the same structure, right? That basically means that there is a one-to-one. There is a one-to-one correspondence between groups where the operation is the same. Operation produces, that's actually a very bad way of actually defining this, between groups where the operation produces the same group multiplication table. Let me just say it like this, okay? Even though I didn't say anything about the table in here. But what's important in here is that if I call this number as gamma, gamma is e to the 2 pi I over n, I can see that the group un is basically the number 1 gamma, gamma squared, and so on, and to the nth power of gamma. But Zn is basically formed from 0, 1, 2, and so on, and to the n minus 1. So as a result, a number k in this set of integers corresponds to gamma to the power k in un. So if I have like, I don't know, the sum of 2 integers in here, and this gives me the third integer modulo n, that's the same thing as saying that gamma to the power k multiplied with gamma to the power k prime gives me gamma to the power k double prime. Okay, so the group operation that you can do in one group corresponds to the group operation that you can do in the other group. So as a result, mathematically, these two groups may look different from each other, but their structure is the same. They are essentially the same group, okay, if you just consider the structure only. So when we are talking about the symmetric groups and whatever, things like that, we usually think of them as abstract elements. And so as a result, what's important for us is the structure of the group multiplication table, because we won't be basically dealing directly with this abstract group. We will be dealing with the representations in the real applications. And for this correspondence, only the structure of the group is important in here. So as a result, we would like to think of these like mathematically different, but isomorphic groups as somewhat the same, right? We don't want to make any distinction between them. All right. So as a result, let's just make this connection. So let's say a group G with an operation O, and let's say a group K with operation star are isomorphic. All right. We say that they are isomorphic. I'm going to show this by this symbol G. I mean, I have to do it like that. This group is isomorphic to that group, or sometimes I'm just going to use, frequently I'm just going to use the sets themselves, if you know what the group operation is, right? If there is a map that relates G to K, and it is invertible, so F is 1-to-1 onto, which means it's invertible. So there's actually an inverse exists, such that if you have like these two elements operated within the group, their images also operated like that. Okay. Okay, so that's basically the relationship that mathematicians usually write down. But that's basically what we mean in here. So that's the group G and that's the group K. So in that case, there's an element G in here that corresponds to some kind of an element, let's say K in here. There's a second element G prime in here that corresponds to a second element in here, K prime. And there's a third one in here that corresponds to K double prime. Okay, let's just do it like that. Okay. What I'm saying is that if G operation with G prime gives me G double prime, sorry, it's not just if, it is if and only if. The implication is both ways. If the group operation on the set K gives me the same group operation in here. Okay. So in that case, I'm not going to make any distinction essentially between these two groups. Usually I'm just going to show them by the same symbol. So as a result, I'm just going to show it like that. Okay. So when the groups are isomorphic, then I'll treat them as the same groups, because you can then convert the one operation to the other kind of operation. Okay, second, right, why did I mention this? I think there's some kind of a conceptual simplification in here. So Zn is an additive group. So to show the operations in here, I have to use a plus sign. I cannot omit it. But I can think of this Zn group, addition modulo n, as a group, as a multiplicative group as well, by using this group isomorphism. So I can form a version of the, let's say it like this. I can find an isomorphic group where the group operation is multiplication. Okay, so it is this one in here. Okay, and so as a result, that's the reason why, because I mean, even if the group is additive, I can think of the group as a multiplicative group. So as a result, I'll be using this kind of shorthand notation for these kind of things, okay? That kind of gives me a power to do these kind of things. So that's basically a nice notational simplification. There's actually a group in here. So let's say it like this. A group generated by an element, by an abstract element, I think I should have actually defined what an order is. But I'm just going to show it like this. So by an abstract element where, sorry about this. Sorry, I'm going to undo this. So I was going to develop a third symbol for this group in here, but let's just do these kind of things. So first of all, we have the cancellation theorem. So let me first of all do this. So I'm going to simplify the notation to that. Okay, so I'm not going to show this O symbol or the, sorry, again, let me forget about this. Okay, so I have said that some groups appear as, come from algebra, from mathematics. But most of the symmetry groups are basically maps. So let's say it like this. We can have groups obtained from functions on some sets. Okay, so we might have a function, for example, from some object into some other object. Usually, the symmetry transformations are of that kind. Okay. For example, in that case, for example, X might be the set of numbers from 1 to n. Okay. And just consider, for example, let's say, so consider, for example, a function from X to X, which is 1 to 1, meaning that that function maps each number to a different number. Okay, which means it is onto and invertible. Since this is a finite set, if the function is 1 to 1, then it has to be onto, and so therefore it has to be invertible. Okay. So we call Sn, this is the symmetric group. So these are basically the set of all invertible functions on X. So I don't know. I mean, I don't have actually a nice mathematical way of actually defining this in the set notation, but let's just say it like this. In that case, Sn together with the function composition in here, so that's the function composition now, is a group called the symmetric group. I'll talk about this group in detail, okay, because this is going to be a very important application. So what's this function composition in here? So it's basically, let's say it like this: if f and g are functions, then f of g is also a function, okay, which is basically invertible. So that essentially means that, I mean, you know that g is a map from x to x, and f is a map from x to x, okay? So by f of g, we essentially mean a map where every element x is mapped first by g into some element, and then by f into another element, right? So you can then think of it like this. So that's the set x, that's the set x, and that's the set x. So for example, one is mapped into some by g, sorry, the element 1 is mapped into g of 1 by the map g, and then by the map f, it is mapped into, therefore, f of g of 1, okay? So we just show this by the symbol like that, right? So where the element 1 is mapped into element to that final element by the map f of g of 1. All right, whatever. I mean, I know that you use this symbol for function composition in calculus. And so as a result, I'm just going to use the same symbol again for now. So this f of g means, right? First, g is applied, then f is applied, okay? So the order where the operation is applied is just from right to left, okay? Just keep this in mind. Unfortunately, mathematicians have some strange notations, so they usually think that f is applied first and then g is applied next in some situations. So as a result, it might be kind of harder to follow their notation. But we are going to use this notation in here. So just keep in mind that in calculus too, by this notation, we actually mean the same thing, right? First, the function g is applied, and then the function f, okay? So all of the elements of Sn are called elements of Sn are called, each one is called a permutation. Are called permutations. As I said, I'm going to talk about these because we need to develop some certain notations in them for them. And the permutation symmetry is a very important symmetry for identical particles. So as a result, this is actually a very nice symmetric group. Usually, I mean, in here, I have just defined X as some kind of numbers from 1 to n. But in reality, these are going to be, for example, particles in an, for example, an electron atom. So these are going to be the electrons in there. So you basically permute the electrons with each other in such a way that this correspondence is 1-to-1. And you basically expect that the physics is actually invariant. So there's some kind of a, I mean, by these maps, we are essentially implying some kind of a symmetry operation in there, okay? And so as a result, we are going to use the group in here, Sn, the symmetric group, as the symmetric group of system composed of n identical particles. So as a result, this somehow appears in naturally in some applications. All right, let me think about this a moment. So that's one example. Another example is this. For example, X might be the set of R cube, for example. So that's the coordinate space. Sorry about this. Why did I say coordinate space? There's no such thing. So position space, for example, for a particle living in 3D space. Okay, think of it like that, okay? A particle living in 3 dimensions. So you're going to use, for example, R cube. I mean, any point in this space as a possible position of that particle, right? So let me also show it like that, okay? So there's this X, Y, and Z axes in here. And then you have a particle in here. So the translation is some kind of a symmetry in here. So that's basically, you just take the particle and then translate by A. Okay, A is some kind of a vector, and then you just translate it to a different location. So a translation by A, for example, is a map. So let me just show it like that. So the translation by A, let's say is like this. This is TA, that's translation by A, is a map on R cube. Why? Translation by A, when applied on X, Y, Z, gives me a new set of points, which is basically related to the old set by these relationships. Sorry about this. Probably I shouldn't have written down that much detail in here. That's why I'm spending so much time in these kind of things. But the essential idea is that the translation operation, in that case, can be considered as maps on, or the transformations of the R cube, the Euclidean space, into itself, right? It's also one-to-one and whatever, it is invertible as well. So as a result, we define the translation group in 3 dimensions. So this basically formed from TA, where A is basically all possible sets of the translations in here. So that's the translation group. Group in 3D, okay? So it has the obvious identity operation. So that's the identity. We have the addition rule, sorry, product rule, sorry. First, we translate by B, then by A. That's the same thing as like the translation by A plus B. And then we have the inverse of a translation, which is basically a translation by minus A, all right? So this basically gives us the structure of the group. Okay. So in that case, the group operation is the function composition, but you can see that this group is essentially the same as the group of the real 3-dimensional space together with addition. So this, as you can think of it as a vector space in 3 dimensions together with addition. So the 3-dimensional translation group is the same, is more or less the same as this group in here, because there's an isomorphism. There's a one-to-one correspondence. Okay. And so as a result, I can also think of this translation group as a multiplicative group as well, but the real operation is like this composition in here. There are also other ways of actually thinking about these operations. The translation operations, for example, I can think of them as some kind of a matrix multiplication. Right? There are nice ways of actually making sure that all of these things are satisfied. I mean, we have the same group structure. If I express the translations by matrix multiplication, this can also be done, okay? So in any case, when we have symmetric groups appear as a set of transformations of some base set X, whatever it is, okay? I can actually give many more examples in here. For the permutations, X was some kind of a set with n elements, but it could have been like n particles, for example. For the translation group, X is just the position space, but it could have been the phase space of that we use in, it's like the 6-dimensional phase space that contains the position and momentum, for example, as a space. So you can also define it in there too, right? So you can actually define them in many different ways, but the symmetric group basically appears as transformations in here. So these transformations are the group elements, basically, the group operations. In that case, the product of the group elements is actually the function composition of the group operations. Okay, just keep this in mind because we usually treat most of these symmetric groups like that, but sometimes we can also describe them algebraically. For example, the rotation group. All right, I'll just keep it short. I mean, in the case of rotation group, just like the translation, this is like a transformation of this 3-dimensional space. But I can express this as the application of a 3x3 matrix. And so as a result, the rotation group can actually be described as as some kind of a matrix group, where the operation is the algebraic matrix multiplication. Okay. In any case, so these are some details which are unimportant, right? Because at the end, I'm just going to look at everything from an abstract point of view. And so as a result, I don't care what the group operation is. What are the group elements? What are these things exactly? I don't usually care. And so as a result, for most of the cases, I'm going to do some kind of an abstractification. Okay, so for example, for rotations, even though I can express rotations as some kind of a 3x3 matrix, usually I'll think that these things as some kind of an abstract element, abstract thing, because these kind of an abstractification sometimes simplifies the discussion, okay? And that's basically what I'm going to do. All right, but in the last few minutes, like 5 minutes, let me talk about these other things that I'm going to do. So the first, let me just do this, okay? So there was a group operation symbol in here, right? Forget about it, just express it. So express group operation symbol. I'm going to call this as a product, sometimes multiplication, because I don't know the difference between these two terms. I'm going to say that I'm multiplying two group elements, all right? But just keep in mind that this group operation might as well be an addition as well, but I don't care, okay? There's an important thing that we call as the cancellation theorem. It says this: if we have like G times H is equal to G times K, then what we can do is we can cancel these. I mean, if there is the same element on the left-hand side, then we can cancel them. And so as a result, we can write H is equal to K, okay? So the proof goes like that. It's very simple, actually. We just write this equation, and then we multiply each one from the left by the inverse. Okay. In any case, so there are these kind of details in here. Normally, of course, we have to first carry out this multiplication and then the other multiplication. But because of the associativity, we can carry out this multiplication. So I know that this is identity. And so I know that the identity multiplied with an element gives you this thing. So as a result, this is kind of the end of the proof, right? In any case, I mean, this is something that we do automatically for algebraic stuff. It's just a statement that, well, that assures us that we can do this in here without any problems, okay? So as a result, if in an equation of group operations, the same element appears on the left-hand side, then we can cancel them. And similarly, all right, for the right-hand side as well. So if we have like, if Hg is equal to Kg, then H is equal to K. Okay, so I just call this as the cancellation theorem. Obviously, we don't have this, right? Note, it is possible that GH might be equal to KG, but H is different than K. So we are going to, I mean, if one element, the same element appears on the left-hand side in here, on the right-hand side on the other part. Yeah, I don't know how to express this. I mean, you cannot cancel these two, right? You cannot have cancellation in here. So as a result, this is something that you have to be careful with. Let's talk about the powers. If I have the product of two elements and so on, I'm just going to show them by the power symbol, right? For additive groups, this is actually particularly awkward, right? In any case, by G to the N, I'm going to imply it's the product of the same element N times. So as a result, you can also think of it like the product of G with G to the N minus 1 and so on. Okay. So as a result, naturally, the product of the nth power with the product of the nth power gives you the product of the sum of these two powers, obviously. Now, we would like to extend this. I mean, this is true for positive integers n and m. But we would like to extend this to negative integers and 0, right? So as a result, I'm going to define the 0th power of an element as the identity. So that's the definition. And the minus 1th power as the inverse of G. But incidentally, we're using this notation to express the inverse, okay? And so as a result, I'm going to use minus 2nd power to mean the square of whatever, G inverse, okay? In that case, you can show that this relationship that I have written down in here is valid for any possible integers. So for any integers n and m. It's not true only for positive integers. It is also true for negative integers as well. Okay, so let me finish like that. And on Wednesday, I'll just continue with this basic stuff. So probably it's going to take me 3 weeks to complete the whole thing.